Okay, here's the thing. I watched the stream yesterday, and I did not realize my fan was like super freaking annoying loud, and that I don't have my noise canceling on. So now there should be no noise canceling. Thank God. Nice thumbnail, Unc. Robert, I like how you immediately see it. Bro's stalking me. Let me check. Does Robro have the goon cam? Does he have the goon cam? Oh, there's a trailer. Alright. Hopefully we get to the goon cam eventually. Making a slur for every Minecraft mob speedrun. Alright, that's kind of fire. Y'all gotta catch me when I'm off stream watching Robro for like 30 minutes. He ranked Minecraft baby mouse and how crackable they are. Jesus Christ. Alright. So, linear algebra. We're back. Ladies and gentlemen, we are back. Yeah. It's like, you know. Back as if we never left. I kinda like that. I've never done full screen, but like I feel like I kinda have to. That makes sense. Alright. Yesterday we finished this entire unit for vectors. So every other lesson, like here, I at least know a little bit about. I have some knowledge and I've probably just forgotten a lot of it. Except for imaginaries, this one is actually new, but like I really don't care much about this. I don't think I'm gonna use this until like a while. I'm gonna skip this for the sake of speeding it up. But this is gonna be the first lesson that I actually like know nothing about. All I know is that it's just a matrix, it's just a collection of vectors. That's literally it. I'm doing homework in a big... Hey, you gotta respect the grind. You gotta respect it. One day, you know, one day you start gooning, the other day you start studying. You know? Or something like that. I don't know what the saying was. Draw a triangle so you look smart. Wait, hold on. Epstein is... I was about to write gay, but like that's kind of unoriginal. Ah. There you go. All right. Here you go. Oh, you can't see it. No. Oh, there we go. All right, let's start. What is a matrix?
This diagram represents the different train routes between 3 cities. Each node is a city, and each
Why is it so quiet?
arrow represents a direct bus route.
Yo, it's so quiet. Okay, I think I have volume master.
To city. So for example, this arrow right over here, I guess would represent a direct We're told this network diagram represents the different train routes between three cities. Each node is a city, and each directed arrow represents a direct bus route from city to city. So
Okay. Different train routes between three different cities. Each node. What's a node? Math node. Is that just a point? No, not you. Wait, there's an idle game about math? Okay, that's kind of fire. What is a node? A point at which a curve intersects itself. What? What's that message on the top right? Nothing. What is it though? Oh, it's called a vertex? Because I use a point. So it's basically just a point, all right? Hey, you never know. I've never used this word before for something, so 40 out of 100 is already a passing grade. 40 out of 100 is fucking ass, bro. I consider like a passing grade to be like 80%.
Example, this arrow right over here, I guess, would represent a direct
Where this is necessary. I think this is one where I feel like I would need it. Not for calc, but for something else. I'll figure it out.
route that starts in city 3 and ends in city 1. While
Okay. There different bus route. I'm so confused. Why are there like 100 arrows? Why is there 3 going to itself?
this would represent a direct bus route that starts
Okay. So there's a bus route here, and it goes back. Okay.
city 3 and ends in city 1. While this arrow that has an arrow on both sides shows a route that both starts in city 3 and ends in city 1, and a route that
end city 1. Oh, so this is where it starts, this is where it ends, and you have to write how many times it ends in city 1. So how many start in city 1 and end in city 1?
That starts in city 1 and ends in city 3. So it says complete the matrix so it represents the number of direct routes between the cities, where rows are starting points and columns are end points. So this is the matrix right over here. I encourage you, if you feel so inspired, and I encourage you to feel so inspired, pause.
Okay. So I guess, okay. All right, sure.
This video and see if you can fill out.
So the first one is 0.
Right, let's do it together. So what would go here? This would be the number of direct routes that start at city 1 and end at city 1.
0.
So if we start at city 1, are there any things that then end at city 1?
None.
Well, no. It doesn't look like there's anything that starts and ends at city 2.
End in city 2. Okay.
2, so that's
there's
1.
3.
We get 2.
But there's 4 over here at the top.
We get 3. And then we get 4, because you can start at city 1 here and then end at city 3.
Okay.
Pause this video and
end in city 3. So you have 1, 2. That's it. Because this one in the middle is only one-sided.
Think about that. Arrow ends at city 3. Not start at right over here. And those color
it's only
at
2.
city 1.
Okay, city 2 to city 1. 1.
Well, if we start at city 2
and then city 2 to 2, 0. City 2 to 3, 0. City 3 to 1 is 2, I think. No, 3, because there's another, forgot about that, sorry. City 3 to 2 is 1. City 3 to city is 1. Okay. Guys, it's 7. My God.
4 incoming routes. City 2 has a total of 4 plus 1, 5 incoming routes, and city 3 has a total of 2 plus 0 plus 1 has 3 incoming routes. So it looks like this would be city 2. City 2 with 5 incoming routes. Which city has the most outgoing routes? Well, then we would just look
How's the most incoming routes? Oh yeah, because we start and end here. And remember that columns are starting points and rows are endpoints. So the most incoming routes, you just add the columns, and then outgoing routes, just add the rows. So I guess for the second question, it's going to be city 1. Wait, what? Answer the question.
city. So that is city 1 with 6 routes.
There we go. All right, cool. Payoffs.
We're told Violet and Lennox play an elaborated version of rock, paper, scissors, where each combination of shape choices earns a different number of points for the winner. So rock, paper, scissors, the game, of course, where rock beats scissors, scissors beats paper, and paper beats rock.
Okay.
And then they give us this elaborate version right over here. When Violet wins, she gets 2 points. When Lennox wins with rock, she gets 3. When Lennox wins with paper, she gets 2 points. When Lennox wins with scissors, she gets 1 point. And if they choose the same shape, nobody gets any points because
I see.
that round.
So Violet just chooses the constant. But if Lennox wins with Lennox decides to change the point system depending on what one she gets. He or she, I don't know if Lennox is a girl or guy name. If both players choose the same shape, nobody gets any points. So obviously the diagonal is going to be 0, 0, 0, 0. If Violet is paper and Lennox is rock, so Violet wins 2 points. Oh wait, that means this diagonal is also going to be 2 points since it'd be paper. Here, these two. And then, what's another one where Violet would win? Paper and scissors? No. Paper beats rock, scissors beats paper. Rock beats scissors up here. So this is also 2 points. Okay. And then, I guess, paper beats rock here. Wins with paper. So this is this is 2 points over here. Then, my God, my voice is dying. 1 point over here and 3 points. All right, bet. What is the last digit of 8,977 to the power of 6? Let me guess. It's probably 6 or 7.
Complete the matrix so it represents their scoring system. It shows the number of points Violet gets. A negative number means Lennox gets those.
Oh, Violet gets. Where rows are Violet's chosen shape. Okay. And columns are Lennox's chosen shape. Assuming Lennox picks her shape entirely at random, what shape would Violet choose to maximize her chances of getting the most points?
Those points. Where rows are Violet's chosen shape and columns are Lennox's.
Oh, all right. So let's just do that. So instead of
2 points,
2, just get negative. Sorry, I don't read the instructions because I'm dumb. So it seems like the best choice is to pick paper. Paper. All right. Cool. Keep saying random shit, chat. All right. What is a matrix, though? I just want to know a definition. I spelled it wrong. Array of numbers, symbols, or expressions arranged in rows and columns. All right. All right. It's like a, yeah. Well, okay, bro. All right. God, wait, hold on. Hold on. Oh my God, bro. All right. I'm back. Had to drink some water. Bro, is there also Matrix? Yeah. I don't know. Hold on. Oh my God, my freaking monitor is so stupid. I'm just changing the brightness because it's super bright. All right. Adam, Ben, and Charlotte are very active on putting this lo-fi music. Are very active on various online social networks. Oh no. This represents a number of different networks on which they follow each other, where rows are followers and columns are followed. Okay. Obviously, you can't follow each other. You can't follow yourself, so 0, 0. Wait, what? Where rows are followers and columns are followed. So Adam has columns are followed. What does that mean? What does it mean exactly, though? If, for example, Charlotte is here and Adam's here. So Charlotte followed Adam 3 times? Oh, the number of different networks on which they follow each other. Okay, so yeah, Charlotte did. So Charlotte does follow Adam on three times. That's literally what it means. Okay, I was like, what? I'm just I know what this is. This is followed. This is follower. I just don't know, like, what does it mean? So it means that, for example, if this is 3, Ben followed Charlotte on 3 different social networks. Something like that. All right, let's see. Complete the interpretation for the box cell, 2nd row, 3rd column. Okay, this one. Oh, it already has a box in it. All right. Ben follows Charlotte on 3 different. All right, see, that's what I mean. I thought it meant there were 3 different Bens and they followed Charlotte. I don't know why. All right. Okay. Which shirt type has the largest total inventory? Oh, I have to add the 2. All right. This is 40. This is 46. This is 47. And this is, what is that? 30, 45. This is 45, I think. So type 3. Hopefully I'm not doing this wrong. Yeah, 45. Alright, cool. Bro, how did a fly get in here? My doors my doors have been closed this entire time. God fucking damn it, bro. Alright. Tom and Jerry playing yeah, you get the point. Complete the matrix. Alright. When paper beats rock, the winner gets 1 point. Okay, when paper beats rock, the winner gets 1 point. When rock beats scissors, the winner gets 2 points. Oh, this is 0. When scissors beat paper, 3 points. If both players are right, this is rock beat scissors. Rock beat scissors, 2 points. Scissors beat paper, 3 points. Oh my god, I'm so stupid. Rock beats scissors. Oh, I forgot about the negative number. I forgot. I keep forgetting, bro. I have to read the freaking instructions. This has always been my flaw because I just want to finish this shit as quickly as possible. A negative, alright. Okay, so we're in Tom's perspective. Alright. Alright, cool. 0. If scissors beat rock beats paper, rock beats scissors, 2 points. 2 points. Here, paper and scissors, negative 3. Alright. Whether they want to answer an easy, intermediate, hard question. The harder the question, the more points. Alright. However, they get the question wrong, they're penalized. Okay. The matrix represents number of points. Alright. If the contestant gets an easy question right, they gain 10 points. Bonus. Alright. Number of train routes, okay. There are 2 different direct train routes going from City 3 to City 1. Alright. Oh my god.
Now that we know what a matrix is, let's see if we can start to define some operations on matrices. So let's say I have the 2 by 3 matrix, so 2 rows and 3 columns, and the entries are 7.
Bro, my freaking phone shut down. Why? Why did my phone shut down? I would eat water and drink food on a daily basis. Congrats. God damn it, bro. Hello, Whirow. Wow, I wonder who that is.
5, negative 10, 3,
My phone's
8,
open!
and 0. And I want to define what happens when I
Finally.
multiply
Let
3
me see my chat.
times this whole thing.
Alright, so
first
I have
of
a
all,
matrix and you can I guess multiplying is the first thing you do. Let me guess. Einstein in talking in chat. Einstein is talking. Einstein says if you multiply a matrix by a scalar, you multiply every single value by it. Einstein's talking right now, and that's what he's gonna do. Oh, what the fuck? Oh wait, no, that's 3 times 3, not 3.3. Oh, whoo, 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 whoo. Bro, doing matrices. Got nothing else to do in life, so it is what it is. Einstein talked to me yesterday. Yeah, see, Einstein's telling you to multiply a scalar by a matrix, you just multiply all the individual numbers. There's no Einstein? Mods banned this guy. That's so fucking annoying, bro. Fucking kill yourself, man. No, I'm just joking. I'm just joking. YouTube, don't ban me. I'm just joking. I'm just joking. His name was Super Duper Evil Guy, so I should say super duper evil things to him. A matrix is a rectangular arrangement of numbers, blah blah blah. You should also make sure you know how to add and subtract matrices. Bro, we just skipped it. What? Okay, it's a next lesson. All right, whatever. Why are we multiplying first? All right, it's cool. Thank you, Quetzal Squad, for the $2. Absolute Cinema. Amen. In scalar multiplication, each entry in the matrix is multiplied by a given scalar. Alright? We'll just multiply each one by 2. Alright. So multiply everything by -3. So you have 12, 6, -21, and -3. Oh, Einstein's talking in chat right now. Alright, chat. -1/3. So you have -1, 1, negative, oh no, that's 2, and -3. Okay, so I have a different one. So -1/4, so that's -20, and y is 8. 12, -3, -6. That also 12? Right. Barbecue bacon burger. -3? Yeah. 35. Alright. How do we add and subtract matrices? As long as the dimensions of two matrices are the same, we can add and subtract them like we add and subtract numbers. Okay, but how do you, what if I want to add that are like, you know, different sizes and stuff? So 3A. Khan Academy, so adding, subtracting, and multiplying and dividing, aren't they like all like the same thing? But that's only if they're the same sizes. But like, what if they're not the same size? Hey, I don't mind starting off easy. I ain't gonna lie, bro. I'm happy we're starting off with a fucking addition, subtraction. I'm kind of happy with it. I can't get anything wrong. 3, -2, -1, 3. Calculations are possible. A plus B, B minus A, C minus D. Wait, what? D plus C. What? Aren't they like the same thing? Okay, they're all correct. We need class of clans, feet, goon, corner. Bro, can you please rethink what you just said and what you just typed on your phone or computer? Please rethink your decisions, bro. -3. -5. Bro, that's like the easiest thing ever. Oh, a zero matrix. All right. Einstein is talking here, and Einstein says that a zero matrix is where every single number is 0. Hey, I ain't gonna lie. It's okay, chat. You don't have to know as much as I do. I'm just really good at this stuff, you know. Oh. I'm just so freaking good, bro. Wait, what? So a 2x4. So it's actually 2 rows. I thought. Okay, so it's actually length times width. All right, cool. O, and so it's not 0. It's just O. All right. Add a zero matrix, so it's the same number. I need help. A plus O equals A. All right. So whatever matrix plus 0 is A. And then if you multiply, then A plus negative A equals 0. I mean, duh. A minus A is 0. That should be pretty obvious. 0A equals O. Okay. Oh, here. Guys, we have the list of properties. Alright. But here's the thing. These all assume that these are the same size. That's the very important thing. Every single one of these rules I should know. But the thing is, A, B, and C have to be the same size. I'm really curious though, what happens if they're not? Do you just not add them? Commutative property. Commutative property is where you can arrange them differently and they're the same value, just like addition and multiplication. Associative property, you can change where the parentheses are and nothing changes. Additive identity, yep. There's a unique matrix where you have A plus 0 equals A, and an additive inverse property, so A minus A equals 0. Closure identity is... Okay, so this is actually a new one. A plus B is a matrix of the same dimensions as A and B. So the sum is the same like size and shit. Okay. Cool. Hashtag... Oh, undefined. Alright. Cool. If the dimensions of two matrices are not the same, the addition is not defined. Alright. Oh, because there's no corresponding entry. So, okay, so you just can't add them? I really thought there was a way to add them. Blah, blah, blah. You get the point. Alright, multiplication. Wait, there's no quiz? Alright. Associative property of multiplication. Okay, so multiplying is the same thing. Okay. Distributive, alright, you distribute. Okay, sure. Okay, identity 1A equals A. 0 times A equals O. C times O equals O because O is an empty set. Should I learn set theory? Nah, I want to get a calculus after this. Maybe by like the stream after this stream, we're gonna go to calc. And then after calc 1, or after we learn some basics, then we switch to another subject, and then we go to more advanced calc after that. I'm not gonna lie, I should have done these streams like months ago. It actually helps me be more productive and shit. Khan Academy is not the best, but I really appreciate Khan Academy for, you know, letting me understand my progress and shit. Because like it's just hard to do it if I just have YouTube tutorials and I have no idea what I'm supposed to learn and what I'm not. Because like, you know, at least this time there's like a proper itinerary or whatever the hell you call it. Girl, can you recreate one man, one jar? Bro. The funny thing, I actually did learn like a tiny bit of set theory. A little bit. Weirdly enough, I don't know anything about matrices, but I know about set theory. No slander will be tolerated. I'm sorry, but like Khan Academy has its flaws. Like the way some of the things they teach is like, I don't know, confuse the hell out of me. Hey, no offense though, Khan Academy is still the GOAT. But you know, we're all human and all that. Is that it, by the way? Okay, so it's like, all right, it's all the algebra rules, which I already know. So
we're told a certain pet store chain has 3 types of dog food, and each comes in bags of 2 different sizes. Matrix A represents the store's inventory at location A, where rows are food types and columns are bag sizes. So let's see,
okay.
Store A, that's what Matrix A is telling us. They're telling us we have 3 different types of food, 3 different types of dog food, and then they each come in 2 different sizes. So for example, type 1 dog food in size 1,
Earthly,
they have 5 bags of that.
The fucking planet of Earth came to my channel. That's how you know I'm Einstein, bro. Nah, I know who this guy is, don't worry.
While type 2 dog food in size 2, they have 9 bags of that. All right, that's fair enough.
Bro fell off.
Matrix B represents the store's inventory at location
football
B.
shorts.
All right, same thing for store B.
Okay, so you have 2 different stores, all right. Matrix C represents how many more or less bags of each type and size there are in location A relative to location B. How many? So matrix C is just A minus B, right? Yeah. All right, you get the point. All right, cool. World, can you watch Dreamy Bowl on stream? Yeah, wait, actually, Bluetooth device, yeah, you gave me an idea. What if we watch the fucking Nera butthole video together on stream and then see if we get, like, you know, YouTube strike and all that? Because it's on YouTube. You know, just wanted to experiment, you know. What if, you know, what if? I'm just saying. I actually haven't watched the video myself. I avoided it like the plague. So
we're told in the beginning of each episode of a certain game show, each contestant.
The beginning of the beginning of each episode of a certain game show, each contestant picks a certain door out of the 3 doors. Then the game show randomly picks one of 2 prize bundles. All right. After each round, each contestant receives a prize based on what they picked. Okay. Matrix A is the first round. Matrix B is the second round. The second round can also be a lightning round. In this case, the prizes are doubled. What? Bro, let me... Okay. The second round can also be a lightning round. In this case, the prizes are doubled. But they're not doubled. What? I'm so confused. Matrix C represents the possible prizes during a lightning round. Represent Matrix C. Wait, I'm confused. Okay, so lightning round is where it's doubled. All right, fair enough. But double of what? Let me read this again. After each round, each contestant receives a prize based on the door they picked and the bundle. All right, so they receive like a random prize of these 6. Matrix B represents a prize in the second round. The second round can also be a lightning round. But okay, but like if you pick bundle 2 and then the second round you pick bundle 1, that's not double. Am I confused? Am I confused here? Complete Matrix. So Matrix C is definitely 2 times something. Maybe 2 times Matrix B? I think I'm gonna guess C equals 2B. Okay, never mind. I was right. You can't blame me for overthinking this one. Like, what does this mean? The second round can also be a lightning round? I mean,
so Matrix C is a scenario where we're dealing with a lightning round. And remember, in a lightning round, the prizes are doubled, but it's the second round. It's doubled relative to what it would have been in the second round. So what it would have been in the second round is Matrix B. So another way to think about it is Matrix C is going to be equal to 2 times Matrix B.
But it says the second round can also be a lightning round. I don't get it. What is this? What does this sentence mean? Thank you for the $5. Add a Skibidi corner where it's just Skibidi toilet giving straight teeth to Tung 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 Sahur for 6-7 hours. Bro, why are there who liked that comment? There 2 people like that comment. Why? Why did you like that? Explain yourself. Bro.
And we know when we multiply a matrix times a scalar like this, times just a number, we just multiply each of these entries by that number. So let's do that. If we take $600 and multiply that by 2, that is going to be $1,200. And that makes sense. We just said for each corresponding scenario, the prizes are doubled in a lightning round. So if the contestant picks door 1, host picks bundle 1, instead of $600, it's going to be $1,200.
Okay, fine. I guess. Okay, fine. I guess word like that.
So pause the video and think about it.
Oh, this a Matrix D? Sure, have a Matrix D for no reason. But okay. A plus B. I mean, that's like easy. Alright, so just basically word problems. Cool. Let me. Fine. I guess I won't. It's too much. Right. Mia owns food trucks at 2 different locations that sell 3 different types of tacos. Okay, you guys are lucky I have my noise canceling because it's really goddamn hot. Oh my god, it's so hot. Oh, it's the worst day ever. I'm gonna melt in here. Alright. 2 different locations that sell 3 different kinds of tacos. Matrix A represents the average daily sales of each type of taco at the location A, with or without an added beverage. Type 1 with beverage is 20. Okay. Average daily sales at this one, right? Matrix B is this one. Matrix C is how many more or less tacos, all right? Mia sells at location A, sells at location A to, wait, what? How many more or less tacos Mia sells at location A compared to location B? Okay. So with matrix A, so it's basically A minus B again. So 0, 25 minus 30, negative 5, negative 25, 10, 15. Yo, thank you, Samuel, for the 10. I think it's UAE currency. Scammer hack report noob. Great choice of words, man. Appreciate it. Appreciate it. Tons. Wow. Very inspirational. Is this pre-calc? No, it's not. Listen to the donations. The donations only just make your voices louder, but not make your voices heard. Because Jesus Christ, man. I refuse to get brain rot, bro. I want to get brain growth. A toy factory has 3 machines that produce 2 kinds of toys. Matrix A represents the number of toys each machine produces in a day. Alright. Matrix B is defined as follows. Alright. So it's basically just 4 machines. Twelve machines instead of 3. Oh, I'm dumb. Because it's each day. I'm sorry. I always get one of these wrong. I fart. Thank you. Bao is a traveling salesperson of raincoats and sunglasses. Bro, you weirdo. For each of the 3 destinations you travel to, he tracks his average daily profit, depending on whether it's a rainy day or a sunny day. Alright. Raincoats here. Sunglasses here. A plus B. So it's just how much he made from selling both. Alright. Both profits. Thank you, Dark. You actually got it. Total number of direct train routes between 3 cities. Matrix B's represent the number of routes out of order. So these ones are the ones in order, out of order. A minus B. What does C represent? Oh, wait, because this is total number. These are the ones that don't work. So matrix A minus B is going to be only the ones that work. Yeah. Alright. On two certain game shows, contestants can choose whether they want to answer an easy, intermediate, or hard question. A harder question, blah, blah, blah. Matrix A represents the number of points in game show A can gain or lose for each type of question. Game show B is for theirs. Alright. Matrix C represents how many more or less points gained in game show B compared to game show A? Okay. So basically B minus A then. B minus 5, yeah. Okay, 12 minus 10 is 2. Negative 2 minus negative 1 is negative 1. Negative 20 minus negative 15, negative 5. 100 minus 80 is 20. 28 minus 30 is negative 2. Right. 0, negative 2. 0, negative 2. I don't want to do this again, bro. Okay, so matrix A represents the number of train routes. Matrix B is the number of bus routes by either train or bus. So just add the two. City 2 is 2 plus 1, 3, 4, 5. 3, 4, 5. 2, 0. This freaking diagram, okay, looks like a freaking angelic structure. I don't know why. Just complete the matrix, alright? City 1 to city 2 has 2, 1 to 3, 1, just 1. City 3 to 1 is just 1. 3 to 2 is 1, 2, 3. City 2 to 3 is zilch. Oh my god, bruh. I always get one of these wrong. City 3 to 1? It's just 1. City 3 to city 2 is 3. 2 to 3. What did I get wrong? City 1 to 3? What did I get wrong? City 1 to city 2 is 1, 2. Huh? 1. City 3 to city 1 is 1. This one has to go back. Chat, what is wrong here? I'm so confused. City... Okay, no other question. 1 to 3? 1 to 3. City 1 to city 3. It's 1 though. This 1 arrow going to 3. Oh my... Okay, I'm blind. It's because of this one. It goes both ways. I'm sorry. Fuck! Damn it, bro. Damn, bro. It's annoying. Damn. Unc can do kindergarten math? How is this kindergarten math? Alright. At the middle of the year, and matrix C is B minus A. So B minus A is just the difference. The change in the number. No. Whatever, bro. Whatever. Next lesson. Where are we? We're in. Right. It has been around an hour. All right. Let's see. Can we finish this entire unit in one stream? We'll see. We'll see. Matrices as transformations of the plane. So we're okay. So earlier we were just using it as like columns and stuff. As like, you know, just a table. But now we're actually going to go to the plane, the Euclidean plane and shit.
In this video, we're going to explore how a 2x2 matrix.
But you know what? Let me look at the questions first. Okay, never mind. I don't know.
Can be.
I'm sorry, Salkan. I'm sorry, Senpai. I will watch your 5 videos.
Interpreted as representing a transformation on the coordinate plane. So let's just start with some examples or some conceptual ideas. So the first conceptual idea is that any point on our coordinate plane here, and this of course is our x-axis and this is our y-axis, can be represented by a combination of two vectors. You could have this vector right over here that goes exactly 1 unit in the horizontal direction. We can represent that as a vector like this, 1, 0. When you write a vector vertically like this, the convention is that the top number here is what we're doing in the x direction.
Wait, what?
And then the
why are we, bro? Why are you writing it like that? Or verdict. Maybe it's just like a new way of saying stuff. I don't know why though. Okay, so it's either one. Okay, so it's just kind of either way. All right. All right. So you can write it either horizontally or vertically, but like I guess the normal thing is to just go vertical. Sure. I guess.
The bottom number, the 0, is what we're doing in the vertical direction or the y direction. So this is the 1, 0 vector. And then this right over here.
I'm using AI overview. Fine, fuck you. Are vectors written horizontally or vertically minus AI? There, okay, no AI. I thought this is not work, bro. This is supposed to. Fine, let's go to Quora then. Get out of here. Okay, I'm kind of too stupid to know this. Fucking bot, bro. Dual space? What is this? I'm going on a rabbit hole. Bro, I don't fucking know anymore. I'm too stupid for this.
What would we call that? Well, that we would call the 0, 1 vector, because it doesn't go at all in the x direction and it only goes up 1 in
I know something about like the I hat and J hat. I know that.
Now, just to feel good that
tiny
any
bit in
point
physics
on the coordinate plane can be represented as a weighted sum of these, let's just pick a point at random. Let's
Both
say
are used in
this
their own
point
way. All right, bet.
over here. Let's call it point A. And you could represent that as a vector that looks something like this. I'll do it as a dotted line. but this could be represented as a positional vector like that. And of course, if we're thinking about it in coordinates, we would just say this is at the coordinate 3, 1. The x-coordinate is at 3, the y-coordinate is 1. But if we wanted to express it in terms of a vector, we could write it as 3,
3,
1.
1. I get okay. We're Einstein guys, so we're not gonna do it horizontally, you know, like a pleb. We're like a noob. We're now a pro, so y'all know that we gotta go vertical now.
Origin
we ain't
positive
playing.
3, in the y direction, we're moving 1 to get there. And you could see that we can represent this as a weighted sum of these two vectors. We can write this as, this is the same thing as 3 times our 1, 0 vector, 1, 0, plus 1 times our 0, 1 vector. 0, 1 vector. And you could see it visually.
What? Oh, okay. I mean, I guess. Right? You get it? 3, 1. Because you multiply, so it's basically, yeah. So you can also write a vector as a transformation of these two simple ones. So 3 times this one plus 1 times this one.
This
whatever
yellow vector that points to point A right over there, you can have 3 of this vector, 1, 2, and then 3, and then 1 of the orange vector. Now, I said that I would explain how 2 by 2 matrices can represent a transformation. And the way that you could think about it is, if I have a 2 by 2 matrix that looks like this.
I wonder, I'm actually thinking, should Robro was here earlier in the stream. Should I ask him if if I can join his SMP for a stream? Nah, bro, that's like nepotism or something. I don't know.
Let me just draw the matrix where the first column is 1, 0, and then the second column is 0, 1. This just tells you what to do with these two vectors. I know this might be a little bit confusing at first, but let's just walk through it together. So the way I've
okay, so you have 1, 0, and okay, so you have these two.
This first column says, what is the transformation you want to apply to this 1, 0 vector, this first blue vector?
Okay.
Well, we're just keeping it 1, 0, so we're not changing it. It's the same. 1, 0 vector here, 1, 0 vector here. Likewise, 0, 1 vector here, 0, 1 vector here. So this 2 by 2 matrix actually represents what's sometimes known as the identity transformation. It maps any point on the coordinate plane back to itself. It doesn't change the points.
What?
But I'm showing this because now I'm going to show a 2 by 2 matrix that represents a non-identity transformation. For example, let me draw the matrix again. So let's say I have the matrix. Instead of 1, 0 here, I'm going to write a 2, 1 here. Instead of a 0, 1 here, let me write a 1, 2. So in this transformation, what we're doing is we're turning this 1, 0 vector into a 2, 1 vector. You're going to see what I'm talking about.
Let me repeat.
3 of this vector.
Why are we just making a matrix of just 2 random vectors? What are we doing?
The way that you could think of this vector, 1, 2,
I mean, I understand this.
2, and then matrix that looks like this. I have a 2 transformation. The first column is 1, 0.
I know how to multiply matrices. We just learned that. But like, why are we making this 2 by 2 matrix?
Represented. This first column says, what is the transformation you want to apply to this 1, 0 vector, this first blue?
Okay.
Represents a non-identity transformation. For example, let me draw the matrix again. 1, 0 here. What we're doing.
2, 1. 2, 1, and 1, 2. Right?
Is we're Well, we go 2 in the x direction, 1 in the y direction, so it's going to look like this.
Any vector is a combination of transform using matrix multiplication. Alright, cool.
It's going to look like
2, 1, and 1, 2.
Sum of the
Okay. It just feels like you're just collecting vectors and then just putting it together. Like, okay, let's just finish the video first.
And the 1, 2 vectors. And so we can now think of another point, A prime, that's not going to be 3 of the 1 zeros and 1 of the 0 1s. We can think of it as, let me write it over here.
Okay, wait, hold on.
3 of the 2 1s.
What?
Plus 1 of the 1 2s. One of these. 1, 2.
6, 2. Wait, what?
So where would that put that now? Well, we're going to go 3 of the 2 1s. So this is, and so that will take me to A prime. This is my new point after the transformation. I go.
What I'm thinking is, let's say we have a vector 3, 1, and that's equal to 3 times, this first vector. And then what I'm assuming he's talking about is we can transform this 3, 1 vector. We don't have to change anything else. All we have to do is just change the numbers in this 2 by 2 matrix, and then it automatically transforms. Okay.
To A prime. So I've gone from
this
point A to this point A prime.
Salkan, you're confusing me. That's a derivative.
Matrix is telling us how to transform.
Sorry.
Now we can do that with multiple points. Now, if I talk about a point here at the origin that was originally at the origin, point B, well, that's 0 of the orange vector, 0 of the blue vectors. So even after the transformation, it's going to be 0 of the 2, 1 vector and 0 of the 1, 2 vectors. So it's just going to stay in place. It's just going to map to itself. So B is equal to B prime. And we could also imagine another point. Let's say right over here. Let's call that point C. Well, point C is originally 2 of the blue vectors and none of the orange vectors. So after the mapping,
that's red,
it'll
not
be
orange.
2 of the 2, 1 vectors and none of the 1, 2 vectors. So 2 of the 2 1s. So if you go 1, 2, and then none of the 1 2s, you're going to get C prime right over there. And so notice, if originally you had a triangle between A, B, and C, let me draw it like this. So originally you had this triangle, A, B, C. What is it now what is it now mapped to? Well, it's now mapped to this big, to A prime. Now you might be saying, Sal, how do you know that the lines map onto other lines? How do you know this transformation didn't all of a sudden make this line squiggly or zigzag? And that's one of the interesting properties of the type of transformation we're talking about. A 2 by 2 matrix will represent a transformation, will another line. And all these two matrix come up with a whole. In a previous video,
Salkan, you're losing me here. Salkan, what was that? We just did like the easiest shit, and then now I don't know anything. What are we doing? Have you understood it? No. You know, maybe let me read this. If we think about a matrix as transformation of space, okay. Okay, how it define matrices on operators like multiplication. It gives actually a nice excuse to draw pretty pictures. This material touch on linear algebra, usually a college topic. See, I'm like so smart, bro. We're doing a college topic. I'm not even in college yet. The idea of a transformation can seem more complicated than it really is at first. So before dividing into 2 by 2, or how 3 by 3, okay, let's go over how plain old numbers can be considered transformers of one-dimensional space. Okay, I like this. 3 blue, 1 brown is spotted. 3 blue, 1 brown spotted. That is a pull, Falcon. I appreciate the knowledge, the ball knowledge you put. I like this video. Oh wait, it's 5 seconds. Okay, maybe. Okay, well, it's 5 seconds long. Whatever. You know what? Whatever. Sure. You know what? Anything helps. What happens when you multiply every number on a line by a particular number? Yeah. I mean, you multiply every value by 2. So for example, if you had 1 here, 1 times 2 is 4. So it's gonna 1 times 2 is 2. Sorry, why did I say 4? We can keep her, okay? Similar, yeah, just, you know, squish the thing by half. Okay. Negative numbers, I mean, just flip the thing, right? You stretch by 3 and then just flip it around. Yeah. Alright. For those of you fond of fancy terminology, these animated equations could be described as linear transformations in one-dimensional space. The word transformation means the same thing as function, something which takes a number and outputs another number. However, while we typically visualize functions with their graphs, people tend to use transformation to indicate that you should instead visualize some object moving, stretching, squishing. So the function 2x visualized as a transformation gives us the multiplication by 2 video alone. It moves the point 1 number on the number line to where 2 starts off. Okay. Linear means one dimension. Bro, what is this? F of x plus y is equal to f of x plus f of y? Bro, okay, maybe not. Maybe we're too stupid for this. Like, we don't need to know the technical definition. That's gonna fucking kill me. Suppose you watch one of these transformations knowing that it's multiplication by some number, but without knowing what that number is, like this one. You can easily figure out which video is being multiplied into the line by following 1. In this case, 1 lands where -3 started off, so you can tell the animation represents multiplication by -3. Oh no, I don't like what I see. Hold on now. A 2-dimensional linear transformation is a special kind of function which takes in a 2-dimensional vector, xy, and outputs some 2-dimensional vector. As before, our use of the word transformation indicates we should think about smooshing something around. Alright, here's some examples. Oh no. Alright, let's get a plane. If it loads. There we go. God, what are we doing? You're killing me, man. Oh my god, bro. Bro, chill. I literally just learned what matrices are like 2 minutes ago. For our purposes, what makes a transformation linear is the following geometric rule. The origin must remain fixed and all lines must remain lines. So all the transformations in the above animation are examples, but the following are not. Oh my god. 3 blue, 1 brown. Alright, chill, alright. You make good videos, but I'm too stupid to like understand like half of them. Alright? Like, come on now. Oh god. No, we're going into 3D space, bro. Oh, but diagonal lines get curved. Okay. Oh my god. Oh, alright, bet. Oh yeah, I remember he did make the essence of linear algebra. I mean, we're just transforming a space. But how? And please don't make... Fuck, man. Imagine you are watching one particular transformation like this one. Okay. How could you describe this to a friend who is not watching the same animation? You can no longer describe using a single number. The way we could keep track of the number could just follow the number 1 in one-dimensional case. To help keep track of everything, let's put a green arrow over the vector 1 nil. Put a red arrow on the vector. Alright, so instead of taking track of 1, we're now taking track of 2 things. Alright. And then boink. Cool. Now it's a lot easier to see where things land. For example, the animation again. Okay. 1, 1 becomes 4, negative 2. Where does the point at negative 1, 0 end up after the plane has undergone the transformation? Alright, so if 1, 1 becomes 4 minus 2, so that's, what is that? Negative 4, 0? What the okay, I guess I didn't know we were adding. I thought we were multiplying. Alright, sure. Wait, what? So 1 becomes 4. And 1 becomes negative 2? I don't fucking know. Wait, how? I just guessed. I mean, you just want me to look at this animation again? Alright, whatever. Can you predict where the point 3-0? I genuinely don't know, bro. I'm just gonna guess. We can see that 1-0 has landed in 1, negative 2. Oh, I mean, just multiply it by 3, right? 1, 1 becomes 4 minus 2. Oh, wait, no. 1, 1, 4 minus 2. On 1, negative 2. And that 2-0 is 2, negative 4. Okay, so you just have to look at the things. Notice a vector like 2-0 starts off as 2 times the green arrow, continues to be 2 times the green arrow after the transformation. Since the green arrow lands on... Alright. What? Bro, we just started! We just started! Bro, we just started, bro. Come on.
Video I talked about how a 2 by
Stop
2
playing.
matrix can be used.
Why are you saying Asian vectors or... We were talking about game shows and trains like 2 seconds ago.
To define a transformation for the entire coordinate plane, What we're going to do in this video is experiment with that a little bit and see if we can think about how to engineer 2x2
What's a
matrices to do
determinant? Bro, I don't know. What are we doing?
some of the transformations that you
Salkan, this is your weakest lesson yet.
be familiar
You really
with,
have to
like
make me go to a third party to a.
rotations or dilations
You know.
or reflections. So this is
It's
a
not even. Stop. Stop playing, bro.
website run by the University of Texas, web.ma.utexas.edu, and you have the
Notice how the sign of the determinant. What's a determinant?
URL here and card over here. This is 0 in the x direction and then 1 in the y direction. Now, the way to engineer a transformation is to say, well, what would that transformation do to these two vectors? And then change the numbers accordingly. So for example, let's say that we wanted to have a reflection about the x-axis. So if you did a reflection about the x-axis, this red vector would not change. It would stay 1, 0. But what would happen to this blue vector? Instead of being 0, 1, it would be 0, negative 1. So in this transformation matrix, if I go from the
So if you go 0 and minus 0, 1, if you go negative 1, it's going to flip. So the dog's going to be
identity
upside down.
matrix here, but instead of 0, 1, it will no longer be the identity matrix. If I put a negative 1 here, and when I press enter, this should flip this blue vector over the x-axis and essentially flip everything.
Consider a linear transformation. F of xy equals AB. As it is linear, f of xy is equal to fx0 plus. Okay. Man, I love Veriscon. It's so fun. Please give me XP. Fuck no.
Everything else with it. So let's try that out. I'm going to press enter. And there you have it. That cute little golden retriever is now flipped over. So that met our intuition. So let's go back to what we were doing before. So that's a reflection, and you could think about what would you do if you wanted to flip the other way across the y-axis. Now, what about a
We
dilation?
just started. Like, don't.
What if we
You can't spoon feed me like terms like this. What's an eigenvalue? We were just talking about game shows and train stations earlier. What are we doing? Bro, we just started. Don't make me do this. Images. Jesus Christ. Okay, maybe not. Okay, here we go. All right. In mathematics, a determinant is a scalar valued function of the entities of a square matrix. The determinant of a matrix A is commonly denoted as det A, or A, okay, whatever. Okay. The determinant of a 2x2 matrix is, okay. Wait, what? No, okay, maybe that's different. That's different. That's different. This is different. Do you have to bring up my goat, Professor Dave, again?
By a factor of 2.
I kind of didn't want to use this
How do you
videos,
think we
but
would modify this
damn.
matrix to do that? Pause this video and think about that. Well, if we want to scale everything down, what we would want is each of these vectors, and especially if it's by a factor of 2, we'd want
missing 8.5 study streams is equivalent to sleeping in a math group for 35 minutes. It's more like sleeping in a math group for like 10 minutes, bro.
each of
You just
these
miss everything.
vectors to be half as long. So instead of 1, 0, and 0, 1, we would do 0.5
Determinant. Okay, maybe it's probably something different. This is like a function, bro. It's a function of a thing. I'm talking about. Notice how the sign of the orientation of the image The arrows denote eigenvalues corresponding. What is an what? What is this? Okay, explain it like a 5. All right, explain why I'm 5 though. Oh, fucking god. Explain like I'm 5. I don't think I'm 5 years old, bro. I think this is like for like 10-year-olds, bro. Okay, what? Okay, fuck you. This is not helping. Okay, Khan Academy, bro. Y'all, you better help me. Asian everything. Linear. Fucking god, do you really want me to have like my own separate shit?
Zero and 0.5. Let me press enter and see what happens. There
Look,
you go.
you get the point. The point is you change the 1, 0, and 0, 1 vectors into another thing. You're going to change everything. You're gonna change the stretching and the squishing and what that. Okay. You get the point. You get the point. It's so easy, bro. That's like the worst rage bit I ever hit in my freaking life. Fucking hell.
In this video, we're going to talk about something called determinants of...
Oh, thank goodness. Thank goodness, man. Oh my god, you were like, bro, the video before
It indeed
has like
worked.
8 different words I don't know.
Of matrices. So I'll start just telling you the notation and how do you compute it, and then we'll think about ways that you can interpret it.
So
Let's
quiet,
give
bro.
ourselves a 2x2 matrix here.
All right.
So, and actually I'll give it in general terms. So let's say that this top left term here is A, and then this one here is B, the top right. The bottom left is C, and then let's call this bottom right D.
I got an email.
Different color. So this is D right over here. The
Never mind.
determinant of this matrix. So let me just call this.
I actually got a few sponsor emails. I declined like all of them. I actually got a sponsor from Cooper. I think it's like another kind of honey. You use it to get coupon codes and you save. It's like Cooper. But I declined it. Not only because it's probably a scam and I'm very skeptical. Their payment is so low, bro. Like they're not paying me shit. Like I know my worth, bro.
Matrix. Let's say that this is matrix A. So there's a bunch of ways to call
Kind of was trolling you. Fucking hell, bro.
the determinant or have the notation for the determinant. We could write it like this. We could have these little, it looks like absolute value signs, but it really means determinant when you apply it to a matrix. So the determinant of matrix A, you can write it that way.
Okay, so so using absolute value, but if it's for a matrix, is a determinant.
You could write it this way. The determinant of matrix A, you could write it that way. Or
Okay.
you could write it this way, where you put these lines that look like big absolute value signs instead of the brackets when you describe the numbers. So you could also write it this way.
Okay.
The top left times the bottom right. So these two, the product of these two, minus, so that's those two right over there, minus the product of these two right over here. So let's
I wonder if I should go. I should move to Professor Dave instead. He's my goat.
just first, before we start to interpret this, get a little practice just computing a
But like, what is it? Okay, so okay, duh. Okay, just solve that. What's a determinant though? Like, what is it? Why are you streaming this? Because it's more fun to suffer together than to suffer alone.
So I have a 2 by 2 matrix here, and we could view
Ah. Oh my god. Freaking AI overview. Math is fun. Wow. All right. Here's an old website. Maybe this will help. A matrix has to be a square, like this one. Okay. 3 times 6 minus 8 times 4, negative 14. Is a special number. See, this is how you this is how you should teach this shit to a dummy like me. Just don't put any special word. Just say it's a special, amazing, beautiful, random number that you get from doing some random thing with this random square. Why? I don't know. Maybe we'll figure it out together. The determinant helps us find the inverse of a matrix, tells us things about the matrix that are useful in systems of linear equation, calculus, and more. Alright? The determinant AD. Okay. It's just AD minus BC. Alright? I can remember that easily. The determinant, if it's 3 by 3, is... Okay, it's that. It's a big thing. Okay, I kind of don't want to do it. Fuck you, I'm not doing this. Okay, let's stick with 2 by 2. It's just a big formula. Oh god. It's called a determinant. So it determines something. But like, why? Let me figure it out together. Inverse of a matrix. Maybe what's this? What is the inverse of a matrix? Just like a number has a reciprocal, a matrix has an inverse. Okay, -1. You don't divide by a matrix. Alright, fair enough. What? Hold on. He's getting really sucky.
view it as having 2 column vectors. So the first...
Hold on. I do not accept moving on in linear algebra without like... I don't know shit. Hold on. Give me a moment. I know who to watch. Get some Professor Dave. I'm sure we can get it from here. I'm sure we can understand it now.
Professor Dave, I want to teach you linear algebra.
He knows a lot about all kinds of stuff. Professor Dave explains.
Please, Professor Dave, please teach me. Khan Academy is really sucky with this.
Now that we are past calculus, it's time...
Wait, what? Wait. Hold on. Whoa. Whoa. Professor Dave, hold on. This is pre-calc. We're not there yet.
to begin to tackle some more advanced concepts in mathematics, and the subject that is typically studied in an undergraduate math curriculum after several semesters of calculus is linear algebra.
No. We're gonna learn it before calculus because we're Einstein, and Einstein takes challenges seriously.
This may sound unintimidating because we already know a lot about lines, and we wrapped up our study of algebra quite a bit earlier in the series. Indeed, in a certain sense, linear algebra is based on very simple concepts, but over the next few tutorials, we will expand upon these concepts to arrive at some incredible fundamental truths about mathematics that we weren't ready to understand before. But first things first, let's start with the basics. At its core, linear algebra is all about linear equations. Linear equations have a lot of real-world applications since so many things have linear relationships, whether in science, engineering, or even economics.
Okay.
Linear equations are a very
MX plus
basic
B,
kind
our
of
favorite.
equation, which take the form y equals mx plus b. We learned many things about linear equations when we studied algebra, and we will assume that this information is already known. So if at any point you feel you need a refresher,
slope, and I think B is the y-intercept.
go back to that portion of the series.
Man, why are you watching this? Because I don't want to do the freaking Khan Academy quiz yet. I don't know
To
shit.
put things into a larger context, we may wonder, why is it that linear equations are so omnipresent?
Because our entire world is linear.
The
It's
reason is that
three
linear
dimensions.
equations embody a happy medium of simplicity and complexity. If we go simpler, looking at the simplest possible function, f of x equals some constant c, this is a line at y equals c,
Oh, no.
having a constant value no matter what the
Don't
input.
look at the other side.
This is
don't look at the
unlikely
right
to
side.
solve too many problems in the real world. On the other side, we
Use
can
the
look at a
book?
quadratic function.
What do you mean use the
f
book?
of x equals ax squared plus bx plus c. As we remember from algebra, solving these can be a little bit tricky. And if we look at cubic or quartic functions,
Oh,
or
boy.
functions of higher degree still, things get quite a bit trickier. Linear equations are right in the middle. Not too simple, not too complicated.
Okay,
Which actually
alright.
end up modeling
sure.
a lot of real-world relationships.
All
To
right,
see how
keep
much
cooking,
structure
keep cooking,
we can
Professor
get
Dave.
from linear equations, consider the following example. Say we need to buy some milk, and we have y dollars. Milk costs m dollars per gallon, so how many gallons of milk can we get? That's easy.
Okay.
We just set up the equation y equals mx.
Oh wait, what? Oh, okay. M times X. So let's say if we have $10 and it's going to be $3 per gallon. Okay, sure. All right.
M dollars per gallon times the x gallons we can afford will equal y,
Oh yeah.
the money we have. If m is $2,
Oh, makes sense. Okay, especially, I think stuff like this is gonna be. It's much easier if I write down the units. The problem is usually I don't. That's why I confuse myself. But in this case, it's very important to write the units because you can check out if the units equal each other and shit.
per gallon, and
Linear algebra
y
is hard, but I'm
$10.
harder.
Since we have $10,
Okay.
10 divided by 2 is 5, and x equals 5. We can get 5 gallons of milk with our $10.
Alright.
Now let's step things up a little. Perhaps we also need to get some orange juice. Let's say that M1
Alright.
is the cost of milk per gallon, and X1 is the number of gallons of milk we get.
Okay.
M2 is the cost of orange juice per gallon, and X2 is the number of gallons of orange juice we get. Y1 is the amount of money we have, and so Y1 will equal M1X1
Okay, I was thinking of this.
plus
this.
M2X2. All of a sudden, there are infinitely many options for what to do, as there are infinite combinations of X1 and X2 that
Alright.
will satisfy this equation. We could buy no orange juice and lots of milk, or we could buy no milk and lots of orange juice. Or more likely, we could buy some combination of milk and orange juice, but we can choose any value for one of these and then calculate the other. Now let's throw another parameter in there. Let's say we can only carry Y2 pounds of stuff home.
Brother, what?
Milk weighs W1 pounds per gallon,
Oh my
and
God.
orange juice weighs W2 pounds per gallon. That means that y2 equals w1x1 plus w2x2.
All right, chill.
Now we need values for x1 and x2 that satisfy both
Chill,
equations
chill.
simultaneously. So things are starting to get a little more complicated, but let's note that each of these is still a linear equation. This means that everywhere we see x, it is not being raised to any exponent. But since there is more than one equation, we can call this a system of linear equations. As you can probably guess, we will be looking at all kinds of different systems of linear equations as we study linear algebra. For this reason, let's
Never
get
mind, chat. I don't think we can finish linear algebra in one stream. Shit, man. Polynomials are also vectors. Maybe he's
some
talking
basic
about like
definitions
just
and
going one
terminology
direction.
out of the way regarding linear equations. From now on, we will consider a linear equation to be any equation in the form a1x1 plus a2x2 plus a3x3 all the way to anxn equals b. So as we can see from the ellipses, there can be any number of terms
ellipses?
of this type, depending on the value of n, and their sum will equal some constant. The a terms are coefficients of any type, and the x terms are not all x. They are actually all different variables. They could be a, b, c, and so forth, or more commonly, x, y, and z, if there are just 3. The main thing that must be true is that none of the variables are raised to any exponent. Otherwise, it would no longer be a linear equation. It would be a quadratic, or cubic, or something else. Also, there are no roots, no trigonometric functions.
Oh, no trig. I like this already. All right, I like this already. No roots, no exponents, no trig. Wait, maybe this will be easy.
None of the other more complicated functions we have learned are going to be involved here. In addition, none of the variables are involved in products or quotients with each other. There is just a series of individual terms
the variables are not multiplied or divided by each other.
Involving a coefficient times a variable. So in that sense, systems of linear equations are very simple. They get complex in other ways, namely due to the fact that if we have 3 equations involving 3 variables, as is shown here, we will have to use certain techniques to solve this system.
All right, bet.
A solution to a system of linear equations will have as many values in it as there are variables in the system.
Okay.
In other words, we need a value for each variable that will make all of the equations true at the same time. And there is no limit to the number of variables or equations in a system. So that is the sense in which systems of linear equations can get very complicated, despite the fact that each individual equation is extremely simple.
All right.
But at first, we will look at very simple systems. Some that
2 equations, 2
equals
unknowns.
-6 and -2x1 minus x2
Isn't this the thing where like you make a third equation
0.
from it?
We can take x1 and x2 to be the same thing as x and y. So we can just solve these for y.
Oh, or you can do that. That works too.
And graph the lines. We will get y equals 3x plus
and
6
just get
and
the
y
intersection.
equation. And the other line, the solution for the 2 algebra, we would arrive at -6/5 for x1.
Whatever. Sure.
If we had 2 lines that were parallel, is of expressing the same from algebra consistent. And when a system has no solution, we say that the system is inconsistent. But we don't have to stop with 2 dimensions, corresponding to 2 variables. We will frequently see 3 variables, and if we have equations, each with an x1 term, x2 term, and x3 term, which can correspond to x, y, and z, these could each correspond with a plane, such as with this system of 3 equations. We can draw the 3 planes and see where they intersect, in this case at a singular point, and the coordinates of this point represent the solution to the system. We could also have an entire line be a solution to this kind of system.
Really?
Or a whole plane.
Or a plane
if
be a
all 3
line, or
equations
whatever.
describe the same plane, both of which would yield infinite solutions. Or we could have 3 parallel planes, and therefore 0 solutions. It doesn't stop there. We could have
Okay,
4
bro,
equations
chill with the
and 4
number of variables,
and that
okay,
transcends
bro.
our ability to represent things geometrically. So we will have to figure out other ways to conceive of such a system.
Okay, bro,
At this point,
chill.
it is clear that a big part of linear algebra will involve learning certain tools and techniques that will allow us to solve systems called, support me on Patreon, now.
Matrix notation, all right. 22 videos, that's not too
Professor
bad.
Dave here, let's enter the matrix.
He knows a
Okay, bro.
Frequently be expressing. So what exactly is a matrix? Let's go ahead and see how these can be constructed.
God, I'm hungry.
Say we have the following system of equations with 3 variables.
Okay.
They all have the same variables, they just have different coefficients, and each expression equals a different number. Since the variables are all the same, it is the coefficients that are relevant. So why don't we abbreviate these coefficients some other way? We can set up a matrix. A matrix is an array of numbers contained in brackets.
Okay,
has-
just for clarity's sake, what's an array? Isn't an array like a group of numbers? Let's see. Just for clarity's sake. In math. All right, cool. So it's just a arrangement of shit in rows and columns. All right. Just for clarity's sake.
As rows and columns of numbers, and we can insert a number of rows and columns that will allow us to express
All right,
the
bet.
coefficients
Numbers in a rectangle.
in this
That's a good way
linear
of saying
system.
it.
The 3 coefficients in the first equation can make up the first row. The 3 coefficients in the second equation can make up the second row. And the 3 coefficients in the third equation.
See, that's the thing. Khan Academy introduced matrices as like 3rd grade level math, bro. I was like, damn, it's easy. And then like 2 seconds later, fuck. World tutor me? I'm being tutored right now. I don't know.
Make up the third row. We have just constructed a coefficient matrix.
All right.
To get
whatever.
a matrix that contains all of the information from the system, we need to add one more column on the right side, which will contain the numbers on the right side of the equal sign for each equation. And this is now called an augmented matrix, which may or may not have a dotted line here to separate this last column
Okay, so
from
this
the
is a different
coefficients.
way of explaining it.
So there we have it, a 3 by 4 matrix, meaning a matrix with 3 rows and 4 columns that contains all of the information that was contained in the system of linear equations.
All right.
We don't need to see the variables because they are implied, and it doesn't matter whether we were calling them A, B, and C, or X, Y, and Z, or anything else you can
Oh yeah,
think of.
because you don't know the numbers, right? You don't know what X, Y, and Z are. So like, there's no way to know. It's just so okay.
What matters
Makes
are
sense.
the coefficients and the numbers on the other side of the equations.
Math is really annoying because sometimes you'll get a definition that if you forget one word, the prof will kill you. But other times you're like, yeah, array just means things in rows and columns.
We should note something
Lol.
important here. We need all of the equations to be in the same format for this to work. If one of the equations had 2 variables on the left side and the third variable on the other side, we would have to bring that third variable over with the others by addition or subtraction.
Okay, so you have to make all of them
Also, if one of the variables is missing from one of the equations,
Oh,
we
just
have
put a
to
zero.
put it back in
Yeah,
with a coefficient
yeah,
of 0.
yeah.
This will not change the equation, but it gives us a coefficient of 0 to plug into our matrix. In general, a system with m equations and n variables will give us an m by n coefficient matrix, because each equation gets its own row, and each variable gets its own
sense.
column. If we then include the constant terms on the other side of each equation, we will get an augmented matrix with dimensions m by n plus 1.
Plus 1. Plus 1.
Let's practice making an augmented matrix one time.
Jesus Christ.
Here are 5 equations with 4 variables. This doesn't look like it's in the right form yet, so let's make some changes. First, let's bring these
All
variables
right.
that
I mean, we know what we're gonna do. Just bring them out of the other side, put zeros, write down the coefficients in a big ass box. Construct an augmented matrix. You know what? It's the first time in the entire stream we're actually using paint.net. Isn't that crazy? It's been 2 hours and it's actually my first time. I'm struggling with trig identities. I'm sorry to say, but that was like 2 streams ago. Whoopsie daisies. So let's do XYZ then. All right, let's bring this over here. Might be the most boring stream. We're gonna get the calculus when Khan Academy tells me I'm finished with calculus. It's XYZ. So, okay. It's going to be 1, 2, 3, 4. There's 3. Okay, it's gonna be a 4x4. Yeah. Three. Okay. 3x minus y, so -1. Z is 0, 1. 4x, 0y, 5z, 6. 1x, 2y, -3, -1. 0, 2, 2, 5, 9. Am I right? 1, 2, -2, -1, 0, 2, 5, 9. Yes! I'm smart.
Professor Dave here. Let's work with matrices.
He knows a lot about
Oh God, I don't like what I'm seeing.
Now that we know how to represent systems of linear equations to solve these systems, we want to find out
6,
whether a
7?
system has 0, 1, or infinitely many solutions. And if there is one solution, we want to find precisely what it is. What are some techniques that we can use to do this?
0 solutions, precisely 1 solution.
The main strategy that we will use involves whether a system has 0 to solve these systems.
Oh, how do we solve the system? All right.
That we will use involves manipulating the system to produce a new system of equations with the same solution as the original one, but is much easier to solve. How can we do this? Actually, this is still the same concept that we learned in algebra. We can manipulate the equations in a system in any way we want that is algebraically valid, meaning we can do anything we want to
But how do you solve it? Like, we don't know any numbers
equation
and shit.
as long as we do it to both sides of the equation.
All right.
Say we have the following system of two.
I mean, if it's stuff like this, you know, isolate one value, isolate x or y, and then substitute in the next one.
Linear equations.
That's like the most elementary way to solve it.
8, which will be 2 by 3.
Or you can do that.
With
All right,
4,
whatever.
6, and -2 in the first row, is to take any equation and multiply or divide.
Oh, this might be a good use of matrices because it streamlines, transform. Oh, wait. My brain is growing, guys. It makes sense. It streamlines transforming many things. Wow. I'm very inspired right now.
By some number. How about we take the first equation and divide everything by 2? This shouldn't change the equation or the system,
all right,
because
divide by
everything
2.
will be in the same proportion. We can also just do this to each term in the first row of our matrix. But just for clarity, let's do both of these things so that we have equations to look at while we do matrix operations. Dividing through, we get 2x plus.
I don't think there's a way to, like, say it. Like, there's no way to say that we're only gonna multiply a matrix on the top row of this 2 by 3.
Plus 3y equals -1, and we alter our matrix accordingly. We can multiply or divide any equation in this manner, or the corresponding row, by any number we want except for 0. The reason we divided by 2 is simple, because now we can use another technique. We can take
Oh, look! You can subtract this 0. So just add these two equations together. So 7x equals
any two
7. So x is 1.
equations in the system and add or subtract them to produce another valid equation that will be part of the
By
system.
the way, study stream 10, I'm gonna do something a little different for tomorrow's stream. You'll see.
This is another technique we learned in algebra. Now with the
2r1
matrix,
becomes
we
r1. Oh, okay.
want to retain the dimensions of the matrix. So let's say we decide that we want to add the 2 rows together. Let's do so and replace the second row with our result. We can achieve this by adding the values in the first row to the values in the second row below. To 5, we add 2 and get 7. To -3, we add 3 and get 0. To 8, we add -1 and get 7. So to summarize, we can add or subtract any 2 rows.
I mean, I guess I still don't see the point of using a matrix in this scenario.
To generate
I
a new
don't get
row
it yet. Like, just do it the regular
without
way.
affecting the solution to the system.
707.
Combining this with the previous technique, where we could multiply or divide any row by some number, we can actually add or subtract any multiple of any row.
We can combine multiples of any 2 rows to get a new one.
To any multiple of any other row to get a new row, or even simply swap 2 rows without changing any of the values, all without affecting the solution to the system. This opens up a lot of possibilities for what to do with a system of equations.
If you can change the row, you can also change the columns. Same thing.
Now take a look at what we are left with in the second 7 equals 1. 1 for y, with zeros in them. If we took this row and divided by 7, we would get 1, 0, 1. And then we don't even have to use any equations. The matrix spits out the answer. So the goal for any linear system, the matrix spits out the answer. So the goal for any
So we want the end result to just have ones and just have 1, 1, 1, 1, or just have the left values be 1 so that we know the exact value of x and y.
Is to write out the augmented matrix and do elementary row operations until each row has a 1 in one of the columns.
Matrix have cool rows. All right, bet.
And zeros in the rest.
We're probably gonna be here for like the next half a week, maybe longer.
Except for the rightmost column, which will give us the value for the variable that corresponds to the position where the 1 is located. When we perform this on a matrix...
Jordan? Damn. What are you gonna tell LeBron fans about this? Is there a Gauss-LeBron equation elimination? I don't think so.
Where the 1 is located. When we perform this on a matrix alone, this technique is called Gauss-Jordan elimination.
Damn.
Let's go through
what's
full
LeBron
example
gonna
together.
say about this?
Take the following equations. X plus 2y plus 3z equals 1. 2x plus...
So you get 1, 2, 3, 2, 4, 7. Okay, put them all. Okay.
Augmented matrix, which will
But, I mean, you can't divide or
be a
anything.
3 by 4 matrix, since we have 3 equations and 3 unknowns. Now, what elementary row operations jump out at us?
I don't know. I don't fucking know, bro. Genuinely no clue. Like, genuinely no clue.
There are plenty of ways
We can add 1 and 2, the first 2 rows, and then minus it by the last row.
we could do this. One thing we could notice is that the coefficients in the first column
Bro,
are
I'm smart! Bro, the only reason Jordan's in there because he didn't want to name another fucking thing about after Gauss. Damn! Jordan got what's the word? I don't
1,
know.
2,
Damn,
and 3.
vocabulary is not my strength.
What if we subtract both the first and second row from the third row to get a new third row?
But why are we eliminating the third row? Like, I feel like he's just kind of picking a random... Okay. So this is a way of solving it. So you get 3 minus 2 minus 1. But remove the last... Are we always going to remove the last row?
3 minus 2 minus 1 is 0.
Right. 7 minus 4, 1.
7 minus
1.
4 minus 2 is 1. 11 minus 7 minus 3 is 1. And 8 minus 2 minus 1 is 5. Getting a 0 is always productive, so that was a good start. What next?
All right, what can we do? So we know that 1 value plus 1 value equals 5. What can we do next? Genuinely no clue. We can divide the second row by 2, minusing the 2 together.
Let's say we notice that the first two coefficients in the first row are precisely half the corresponding second row coefficients. So what we can do is subtract twice the first row from the second row.
Oh, or there's that also.
To get a new second row.
The goal is to somehow get 0, 0, 1 on the last row. So you can use that row to cancel the columns above it. Okay, so it seems like you remove the row that you're putting in first. So for example, like this third row,
2 minus 1.
You get the third row, you minus it from the other two, but remember, you put the last row as your first thing, as the thing you're concerned of. And then the result will replace that row. So this one, you get the second row, you minus it by 2 times this one, so you get 0, 0, 1, 0. Okay, you have this. You have this value is 0. And then what next? Maybe we can take the first one and minus it from 2 times the third one, so that this 2 is removed also. Wait, what?
0. That was a very productive move because we have just solved
Z is 0
for one of the variables. Z must be equal to 0.
Oh, if Z is 0, that means this 1 is 0. And this also
Now
is
we
0.
are in great shape to solve for x and y.
All right. He's teaching this kind of weird low-key. This is a specific process called RREF, with specific steps he's guiding through without saying the steps explicitly. What is... row reduced echelon form. TV program, what? Oh, there's a calculator. So he's doing this. Row echelon form, if it can be obtained, Gaussian elimination. Every matrix can be put in row echelon by applying a sequence of elementary row operations. Okay, so just keep doing row operations until you get this. Okay. God, linear algebra, bro. This is harder than I thought, bro. Oh God.
Let's subtract the second row from the third row to get a new third row. Because that will...
What?
Let's subtract the...
That's this one minus R2. This one minus R2. 1 minus 1, 0, 5 minus... Okay.
second row from the third row to get
so you have to keep doing row operations. Okay.
new third row. because that will get
And then y is 5.
rid of
Okay. So now we can do it like the first row minus 3 times the second row minus 2 times the third row. Right? Are we being for real on God? R1 minus 2R3. Okay, so we isolate this one. And then minus 3. Oh, what did I say? Oh, what did I say? Oh, what did I say?
row
That's
to get 1, 0, 0, negative 9.
This is definitely a thing where like you can learn this. You can shortcut this.
Just for the sake of aesthetic, let's swap the position of this. Leaves us with our solution spelled out for us nice and easy. X is,
All right.
once again, we
If the solution were inconsistent,
could have ended up with no solutions if the system was inconsistent, or we also could have ended up with infinitely many solutions. But in this case, we got just one. There is a way to tell how many solutions there are once Gauss-Jordan elimination is complete, which will be the case once the matrix is in
this is what you said. RREF.
reduced row echelon form,
Echelon. I said echelon. Freaking dummy.
which can be abbreviated this way.
RREF of M. All right, bet.
A matrix is in reduced row echelon form
Echelon.
when any row with non-zero entries has a 1 as its first entry. This is called a leading 1.
Do you see if you have 1, 1, and the rest zeros in a row? Those rows become useful to cancel the stuff below. It's so boring. I'm surprised you weren't bored for like the rest of the stream. bro.
Wherever there is a leading 1, all the other entries in that column are 0.
There's basically one of this equals some value, and then the rest of the column is 0.
The row above that is further to the left. Once we have a matrix at the
Okay.
rank
Yo! So this is a way to find XYZ. You know, if we have this. Alright, bet. I can do that.
the rank is
Rank is equal to the number of leading ones. So rank is equal to the number of columns and coefficient matrix, at most one solution. Wait, what?
Jordan elimination is complete, and we can look at the
He spare you with the influence solution. Okay.
rank of this matrix. The rank is the number of leading ones.
3.
If the rank is equal to the number of columns,
If the rank, so there's 3 leading ones. There's three, the rank 3 or something? Number of columns. So there's 3 columns, 3 ones. So that means there's one
in the
solution.
coefficient matrix, the system has at most one solution, meaning this will
Yeah, this is kind of light. Oh, come on, bro.
typically result in a unique solution. If the rank is less than the number of columns,
So if the rank is less than number of columns, so if there's only 2 ones, then it's infinitely many. So I'm gonna guess if there's more than 1, then there's none.
the augmented
Oh,
matrix.
okay. Sure.
So as we can see, elementary row operations are no different than what we learned in algebra. It is just that we are applying them to a matrix and getting a solution for the system that does not require manipulating equations by using Gauss-Jordan elimination. This may seem arbitrary right now, but let's comprehension.
Okay, alright. Chat, watch me become the absolute smartest being Einstein-ass person in the world, bro. Y'all are not gonna believe me when I say this, bro. Y'all are not gonna believe how fucking smart I am now that we have this. Alright, where do we start? We can do this row. Let's just say this is 1, 1, 2, 3. Let's do 3, minus 2 plus 1. Let's do that. So now I should really do this. So we have 1, 1, 1, 5, 2, 3, 5, 8, and 4 minus adding these two. All right, we have 1. Oh god, there's a negative. Negative 4. What was that? Negative 1. Oh no. Wait, I don't want negative numbers. Maybe that's not solution. 2 minus 8. Oh god, it's all negative. I'm so smart. First step, make everything even harder by adding negative numbers. Okay, maybe not that. I mean, I could technically, but I don't want to deal with negative numbers. Let's not do that. I feel like it would be a little. I think would it be harder though if we dealt with negative numbers? Wait, let me go back. Yeah, this would be 0, bro. Hell nah. Okay, where do we start though? I want to change this third row. But with what? We can do 3 minus 4 4. You know what? Maybe not row 1. Let's do Let's do row A, row B, row C. How about that? That's better. There you go. So let's do C minus 4A. That should be better. So this would be 0, negative 4, 1, and 2 minus 20, negative 18. Okay. Okay, we just have to keep doing this until we finished. What do you want to do now? We can do We can do 2 minus 1. We can do B minus A. So this will still be 1 1 1 5. But now that we do B minus A, this will be 1 2 5 minus 1 4 3. Okay. Zero, negative 1, no, and maybe it should be 2A, so this will be 0. Fuck. Okay, let's not do this one. I think you guys can see. Kinda. There you go, that's better. So if you do B minus 2A instead, this will be 0. Just get as many zeros as you can. 1, 3, negative 2. Okay, negatives doesn't matter. We just have to get as many zeros as we can. All right, what next? What can we do? We can do again. Oh wait. Oh shit. Okay, I'm getting it now. Oh, but what if I do 3A? If I can do A, what if I do A minus B? If I do A minus B, Okay, hold on. How do I do this? A minus B. This will still be 1. This, instead of... What the heck is my... 1 minus 1, which is 0. 1 minus 3 is negative 2. Negative 2. 5 minus minus 2 is 7. Why are you streaming yourself studying? It's fun. It's fun, that's why. What the heck? Fuck. We can add these two. We can add these two. So now we would have a 1 here, a 1 there. No, but we're back to where we were before. Oh my god, bruh. We're just getting we're going in the opposite direction. How did Professor Dave just like so effortlessly like figure out? Maybe just give an easier example. Because he just did one step and then now Z is just okay. Alright, you know what? Fuck it. Let me try again. We're not going anywhere here. Where do we start? Okay. We can let's just write all our steps here. C minus B. Row C minus row B. So we have 1, 1, 1, 5, 2, 3, 5, 8. And we're gonna do C minus B. 4 minus 2, this, minus 3, 0, negative 6. Okay. And then next, we're going to do B plus C. We're gonna get B and then add C to it. Alright, so this one will be 4. This one will be 3 plus negative 3, 0. 5 plus 0, 5. 8 plus negative 6 is 2. Alright. And then we can do B minus 2C. Wait, what? What was I doing earlier? Oh. We can do B minus B. This is 0, but negative 5. What? What the fuck? Okay. I mean, technically speaking, we can do C minus 2A. That's also an option. So this is 0, this is minus 1. This is negative 2. Okay, fine. Let's just do that. C minus 2A. 0. This is going to be negative 5. This is going to be negative 2. Negative 6. Minus 10, which is negative 16. Okay, I think we're going nowhere though. But you know what? Let's not give up. Like, how do you just, like, do you just have to just randomly do this until you get the right thing? Let's do for second row minus, let's do second row plus, I guess, let's do minus 2a. Let's do it to the second row also, b minus 2a. So this is 0. This is 1. This is 3. 8 minus 10, negative 2. Okay, I guess. Oh, wait, okay. Now what? Let's do a minus b. A minus b. So this is 0. This is 1 minus 0. Okay, it's 1. Phone, stop turning off. So you figure the steps out. Motherfucker, bro. This is 0. And a minus b. So negative 2. And this is 7. And then add these. We can do c plus a. So this is 0. So this is 1. Negative 5 stays the same. This is 0. C plus a. So this is negative 9. Bro, we're not getting anywhere. We're literally going nowhere. We're going in circles. Okay, I guess a plus b. No, because it's gonna be 1, 1, 1. We're going back to like literally where we started. We have to remove all the ones. Bro, I'm so lost. We can do b plus a, which is literally just reversing this step. How do you fucking do it? Do you want advice? Yes! I've been stuck here for like 10 minutes doing God knows what. Yes, please. Pretty please. Fuck. I'm gonna restart. This is not it. I only want to do the first step. To get all the zeros under the 1 in the upper right first. Under the 1 in the upper right. Okay. 2, 3, 5, 8, 4. Oh, C minus B. So C is minus B. 2, negative 3, 0. No. Restart. 1, 1, 1, 5, 2, 3, 5, 8. Okay. C minus B. So this is going to be 2 minus 3, 0, negative 6. What are we doing? You're going in circles because this shit is it's a fucking puzzle. just have to like go in random ass directions. Maybe we can do b minus 5a. That's also an option. B minus 5a. So 2 minus 5, which is negative 3. 3 minus 5, which is negative 2. 5 minus is 0. See? 5 minus 5 is 0. 8 minus 25 is... What is 25 minus 8? 16? No, 17. Negative 17. One good way to think about it is, what do I need to make that 4 a 0? So you need to add my negative 4. Make that 4. Alright, we have 2 zeros. That's pretty good. Now we have to isolate these other two. Oh, I see a common denominator. I see this. So we can do... What do I want to do? Well, since these two are 0, okay. Thank you, Ellie. Make 2 of them 0 so that you can do crazy things. So 3 of them plus 2. We can do 3c plus 2b. That's also an option. So 3c, so 6 plus 2b, which is 0. 3c, so it's negative 9 plus negative 4. Negative 9 plus negative 4. 13. Negative 13. 0. 3c, so that is negative 18 minus 34. What is that? 54. 52. 52. Yeah, 52. Okay. What is 52 divided by 13 though? I don't know. 26. 4, right? 13, 4, 12, 5. Ha 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 ha. Ha 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 ha. Alright. This can be 1. They're both negative, so just divide both sides by negative 13, so this is 4. Okay, alright. Appreciate it a lot. Another good way to think about it is... Alright, so let's write it here. C divided by negative 13. When it comes to letters, all you really need to care about is turning them all to X. That's it. All letters are just X, but more complicated. Wiring elementary. Your rage bait is not working anymore, bro. We're not doing this again. So 1 is 4. Okay. So we have this value. Y, or x2, or whatever. So now what? We can do b plus 3a. We can do b plus 3a. But this will be 0. Why would you want this to be 0? We have this already. All right, now we can do where this one equals 0. So we can do b plus 2a. Let's try that. B plus 2a. So negative 1, 0, Oh wait, hold on. But let me look at this again. No, why would I change it? If we already know the value of y is 4, we can just substitute it here. If you add your third row to any other row, will the first column change at all? Oh no, it won't. Damn, because we already have 2 zeros here. Okay, 0 is very good. So we can do C plus... No, we can do B plus 2C. Right? B plus 2C. So this will be nothing. This one will be 0. Right? Yeah, negative 2 plus, yeah, 0. 0. Okay, so once we have this, then... So solve everything to get the okay, first step, try to get 2 zeros in the same column. Next step, try to get at least one row to have just 1. Next, the next operation should use this as adding or subtracting something to isolate. All right, bet. So you have negative 17 plus 2c. The negative 17 plus 8 is negative 9. So next step is going to be b divided by negative 3. So this can be 1. This is 3. Oh! All right, we're getting there. Number 7. Minus this one, minus this one. All right, now we can just do A minus B minus C. A minus B minus C. So this will be 0. This will be 0. And then it's going to be 5 minus 3 minus 4. So 2 minus 4, negative 2. Oh, we did it! We did it! Oh my god, thank you so much. So 1 0 0 3 0 1 0 4 0 0 1 negative 2. That's the answer. Oh my god, bro. Absolutely no help needed. I'm just kidding. We did it. Oh my god, it took 7 steps. It took 7 steps to solve it. Damn, bruh. This shit hard. Alright. Tell me the answer. Tell me the answer. What's the answer? X is 3. 3, 4, negative 2. Yes! 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 Damn! Jesus Christ. Alright, so first step, get try to get 2 zeros in one column. And then try to get one of the answers, and then just the next 2 should be easy. Yes, alright. Thank you so much, guys. Alright. So it's like that. Is it 8 steps? I think I did it in 7 steps. Oh yeah. I don't know what I did wrong. You get the point. 7, 8, 6, 7, whatever. This is freaking crazy.
It's Professor Dave. Let's add matrices.
All right. All of this we should know already. So that's crazy. We did like we just solved like some Michael Jordan thing before he does like the freaking okay.
We now know what matrices are. They are
Wait,
simply
by the way,
arrays
how long has
of
it been? I
numbers.
think I'll end the stream soon. Damn, it's been 2.5 hours? I don't know.
That are often meant to represent the coefficients and constants from a system of linear equations.
Okay, let's finish this one video and then I'll end the stream.
We learned about how to
What
manipulate
math is that? It's in the title.
these to solve such a system of linear equations.
You got the calc?
But for
I
a
got
little
the
bit,
calc.
let's look at matrices on their own and describe some terminology we can apply to them, as well as some simple operations we can do with multiple matrices, starting that may come in handy. We know that any matrix will have some number of rows and some number of columns.
Yep.
If the number of rows and columns
Square
in a
matrix,
square
'cause it's-
matrix, the entries going from the top left
These numbers comprise.
down. In a square matrix, the entries going from the top left down to the bottom right comprise the main diagonal of the matrix.
Okay.
We can refer to a matrix as a whole as a diagonal matrix if all the entries that are not part of the diagonal are 0.
All right.
This is the situation we are trying to get with an augmented matrix when performing Gauss-Jordan elimination, where all the entries on the main diagonal are 1 and the rest are 0, apart from the rightmost column. And if we are just looking at a coefficient matrix that looks like this, we can also call this an identity matrix.
Okay, this one actually makes sense because it's a matrix that literally just shows you what x, y, and z are. Or x1, x2, x3.
Then some other possibilities. A square matrix is called an upper triangular matrix if all the entries below the main diagonal are 0. And it is called a lower triangular matrix if the opposite
This is
is
so
true, with
random,
the
bro.
entries above the
Yes,
main
sure. We will
diagonal
make a term. We will make a specific term for when there is a 0 in row 2, column 1, row 3, column 1, and row 3, column 2. Yes. Are people who are gifted membership allowed Discord? Yes. Everyone who has a membership can join. Just input your name, and if it's in my list that YouTube gives me, then it's fair game.
equal to 0.
The answer is 6, 7.
There are
I
also
agree.
matrices consisting of just one row or column, and these have special names. A matrix with a single column is called a vector.
I mean, makes sense.
Matrix with a single row is called a row vector.
Let's not call it a vector.
Typically,
Right.
when using the word vector in this context, a column is being specified. It is common to list the solution of a system of linear equations as a vector in this manner, such as the following, which clearly shows the values of x, y, and z.
All right, chat. Starting from this day on, I'm going to notate every vector using a column. Why? No particular reason. It just makes me look smarter and makes people think, oh, I know linear equations because I know linear algebra because I write the numbers top to bottom.
We can even represent systems of linear equations themselves using vectors. Take this system of two equations, 3x plus y equals 7 and x plus 2y equals 4. Apart from generating an augmented matrix, we could use individual vectors to represent the coefficients for each variable. First, we generate 3 separate matrices.
So the linear equations can be represented with vectors. Also, so vectors is just one column.
One with the x terms, plus the second with the y terms, and the third with the constants
All
on
right.
the other side of the equal sign. Then we take x and y out of the first two.
All
and we
right,
are
because you
left
can
with the equal
divide.
sign.
You can divide.
Then we take x and y out of the first two, and we are left with the vector 7, 4 as being the sum of a scalar multiple of 3, 1, and a scalar multiple of 1, 2.
All right.
This is called the vector form of the linear system.
All right.
This also outlines some basic operations we can perform with matrices. Given that we pulled a scalar out of 2 matrices to do this, we can also do the reverse and perform scalar multiplication. This is very simple. If we have a
Can I beat math? Imagine Imagine I do a video that's like, can I beat Khan Academy while beating myself? Can I beat my Calc 1 test while beating myself? A. It's kind of a fire idea.
scalar times a matrix. We just multiply every entry in that matrix by the
See,
scalar.
this is the thing we first learned. It looked like matrix was like the easiest thing ever. But okay, sure, give me Michael Jordan equation to that freaking kills me.
So if we have 2 times this matrix, we just double
Andrew Tate?
all the entries,
Yes.
which will work the same way regardless of the dimensions of the matrix. But we can also add 2 entire matrices together. In order for this to work, the 2 matrices must have identical dimensions. That means the same number of rows and the same number of columns.
Yep.
The reason this is the case is that in order to add 2 matrices together, we just generate a new matrix, and each entry is simply the sum of the entries for that specific position in the other 2 matrices.
All right.
Take, for example, the following 2 by 3 matrices. 1, 2, 3, 4, 5, 6, and then 7, 3, 1, 5, 3, negative 1. The sum of these matrices will be a new 2 by 3 matrix. For the first entry, we
Just add.
together,
You get the point.
subtraction.
Subtraction's the
series.
same thing. Yep.
Not subtracting one matrix
Subtraction. I mean, because subtraction itself is not commutative.
from the other will be quite intuitive.
I mean, do we really? Let's skip this one. We already know this. We just did a quiz on this. We're like Einstein already, bro. All right. I'll just save this to my library. I'm like, oh, this is a courses tab. All right. Can I actually do the quiz, or no? What the fuck? All right, there we go. What?
Welcome home, Columbia. Beautiful, beautiful. Discovery 4 computers now have primary control of critical vehicles.
This one. A reflection across the line y equals x. No. If it's over here, then instead of 1, it's negative 1. Right? So it's a reflection across this one. Okay, well, I still don't know. Fine, this one.
Beautiful, beautiful.
I'm gonna leave, bro. Fuck, man. 2 seconds on row operations. I know, right? Fuck me, man. Whatever. We'll do this tomorrow. I'm sure we can figure it out. I guess. Professor Dave, man. Professor Dave, but you know, you can't just teach me Michael Jordan in 10 minutes, you know. You kind of because it kind of made me feel like you can just go randomly and just do it, but no, you have to think about every step. It's like you want me to play a game of chess by just saying just take the king. But okay, sure, go ahead, I guess. But yeah, we'll see you guys tomorrow. Pretty good stream. We're actually, you know, on that grind, almost 3-hour study. You know, we started off doing like 1.5, but like, you know, our brains have been growing and all that. Hello, world. Hello, Goosenator. I don't know if it's your first message, but kind of awkward. Kind of awkward. Because I'm gonna end the stream in 5, 4, 3, 2, 1. Thank you everyone for watching, and thank you to the people donated. Appreciate you tons. Hey, getting money from studying, bro. Hey, that's a good reason to keep doing these streams. I ain't even gonna lie to you. But yeah, see you guys tomorrow. And I thought trig was painful, but we're in for a ride here.